All right, so everything we've talked about up until this point, the circular motion we were dealing with was uniform. Okay, that is that the speed or the magnitude of the velocity did not change at any point in the circle. Vertical circular motion is different because now gravity plays a part, right? So if I've got my ghetto physics demo going here, okay, you can see that in this vertical circle, there are spots where the tape moves slower than others. Okay, where does it move the fastest? At the bottom. Where do I have to pull the hardest to keep it in the circle? The bottom. Okay, at the top, which way is gravity pulling it? Down. In fact, look at the string. When it's at the top, the string goes slack. Okay, at the bottom, gravity's pulling it out. Its inertia wants it to go away. That's where I have to pull the hardest. So if you're on a roller coaster in a vertical loop, where are you going to black out? At the bottom. Okay, the bottom's where you're going to feel the heaviest. That's where the most forces are going to be acting on you. Okay, that's where you're most likely to black out. Same thing with a fighter pilot. When they pull out of a dive, it's at the bottom of the dive where they feel the most G-force. Okay, not at the top. If they're going over the top, that's not nearly as bad. Okay, but at the bottom of the circle is where you feel the heaviest. Okay, and where you're most likely to experience a blacking out sensation. Okay, so for vertical circular motion, first off, it's not uniform. Okay. We're going to look at the forces that contribute to vertical circular motion. They're really just gravity and normal force, and that's it. Okay, and we have to remember that centripetal force really is just the net force. Okay, which is why we calculate it by going forces in minus forces out. Okay, that gives us a net force towards the center of the circle. All right, so we have to remember that FC really is just the circular net force. All right. Sometimes you see people try and do this loop-the-loop trick on a bike. There's even one that has like cars. It's like the Hot Wheels ones you had when you were a kid, the tracks. They have that for real cars. Okay? And so people will go through these loops with real cars. The trick is that you have to be going fast. Okay? There's a minimum speed that you have to attain in order to stay in the circle. If you do not attain said minimum speed, what will happen? You will fall out. And if you don't have that minimum speed, you fall out. Okay. Now, obviously, you wouldn't achieve this like Homer did by driving straight up the circle. Okay. You would drive around to build up speed first, and eventually become more and more vertical as you went. Okay. But you have to achieve this minimum speed because the forces change as you go along. It's not so much that the forces change to different forces; they just change their direction. Okay. At least in reference to the center of the circle. Gravity's always pulling down, but when you're at the top of the circle, it's acting as a centripetal force. When you're at the bottom of the circle, it's trying to pull you out of the circle in the opposite direction. Okay? So at the bottom, the circle has to push that much harder to keep you in it than it does at the top. In fact, if you go just fast enough to stay in this circle, you don't push on the circle at all at the top. Okay? You're just a projectile and you follow an arc that has the same radius as the circle, right? So how would you feel then at the top? You would feel weightless, okay? You'd have a feeling of apparent weightlessness, all right, if you were going just fast enough. Now, does the roller coaster go just fast enough or way faster than it needs to? Yeah, and so you feel pushed into the circle even at the top. If you go faster than that minimum speed, yeah, you are going to feel still heavier. Okay, but if you go just the minimum speed, then you'll feel actually weightless. Okay, and the same is true going over the top of a vertical circle. If you go over the top of a vertical circle, then you can also experience a feeling of apparent weightlessness. You've probably felt this if you've gone over a hill in a car and the hill was kind of sharp, you went over it kind of fast. Okay, you get that feeling like your insides are moving upwards a little bit. It's because they kind of are. You're attached to the car, but they're moving up with their own inertia, right? You're still seat belted to the car, so you stay put, okay? And your insides try and move upwards. Okay, you get that sensation of, oh man, I feel a little lighter. You do, because you are a little bit apparently lighter. Are you actually lighter? No, but you feel that way. That's why we often refer to normal force as apparent weight. You want to write that down. It's the weight we feel. Under most circumstances, it's the same as our actual weight. Okay? But movement and paths and things like that can alter that to feel different. Like if we're in an elevator, okay, the elevator's accelerating upwards, we feel a little bit heavier. If it's accelerating downwards, we feel a little bit lighter. Okay, so normal force is what we call our apparent weight. And under certain circumstances, it can be 0, and we would feel apparently weightless. Okay, we get a sensation of apparent weightlessness. All right, everybody follow me there? All right, so looking at the forces in this circle, okay, at the top of the circle, gravity would pull into the middle. If I'm going faster than the minimum speed, I would also have the track force pushing me towards the middle because my inertia would want me to leave, but the track would push. Okay, so I could have 2 forces pushing me back towards the middle. All right, at the bottom of the circle, gravity is trying to pull out. Same size. Gravity's magnitude doesn't change. It's just its direction with reference to the center. Now, the normal force has got to push which way? Yeah, up towards the center of the circle. But it's got to push a lot harder than it does here because it's got to counteract gravity now. It's not working with gravity, it's counteracting it. That's why you always feel heavier at the bottom of the circle. The normal force pushes way harder there than it does at the top. Okay, here at the side, okay, at this, we never do any with the side, but okay, at the side, normal force pushes in, it's acting as the centripetal force. Gravity's pulling this way. It's perpendicular to the circle. It doesn't even matter. It's not in or out of the circle. It's perpendicular, and it doesn't even come into play. All right, everybody with me there? All right, the one spot we haven't looked at is going over the top of the vertical circle. So now I'm on top of the circle. Which way does gravity pull? In. Okay, so gravity's pulling in. Which way is normal force pushing now? Up, out of the circle. So if I'm going over the top of a vertical circle, normal force pushes outwards. Okay? If I go fast enough, I'll lose contact with the track and I'll feel weightless. Okay? This is how NASA's Vomit Comet works. Okay, that's the one where they shot the scene that we watched there with the pen floating. Okay, that's how it works. It just makes vertical circles in the sky like this. All right, when it goes over the top of a vertical circle and is on its way down, everyone inside feels apparently weightless for about 30 seconds. Okay, and then they have to pull out of that dive. Okay, during that time, they feel heavy, like really heavy. Okay, during that part of it. All right, then they get back up over the top of that circle, okay, and they feel weightless for a little bit, and then they do it again and again. So they call it the vomit comet because that kind of motion really leads to people puking a lot. Okay, all right. In fact, we found this really cool thing. Mr. Dickey and myself found this video. It's and when people have heard of the musical group OK Go. Okay, they do like the most incredible music videos. They're all like planned out to the nth degree, okay? And they did this one inside a zero gravity trainer, right? And it looks really, really cool. So I'm going to show you first the video, and then I'll show you the how they did it, because there's a lot of good physics in that one as well. So forces are going to change throughout that vertical circle. Going over the top of a vertical circle, I will feel lighter. I have to go fairly fast to feel weightless, okay? But at any point going over the top of a vertical circle, I'm going to feel lighter because Fc equals forces in minus forces out, okay? If the faster I go, okay, the less normal force becomes and the lighter I feel until it's 0 and I feel apparently weightless. Everybody follow me there? Okay, that's why eventually you can jump off of a rounded top. Okay, we actually had some kids that got suspended for it, and he broke his car. When we first moved into this building in 2006, a kid took a run at that crosswalk, you know, the big bump. Okay, I mean, luckily there was nobody around, but he took a run at that bump and launched the car. Okay, didn't launch it a lot. Like, we're not talking like the Dukes of Hazzard or anything like that. Okay, he just, you know, he got about, I don't know, maybe 2 feet worth of air. Okay, but when he came back down, of course, it was a small hatchback, like a Hyundai, and there were like 5 people in it. So when he came back down, he smashed down onto the ground, and transmission hit the ground and ripped out, and that was the end of the car. What's that? Yeah, same thing. Yeah, you got to be careful. Yeah. Okay. But this, yeah, and so you can do that if you hit something like that fast. Now, obviously, it's pretty hard in a car to do that, but you can, if you go fast enough, cause this circle now to not have this radius, but to have a larger radius. Well, if that radius is larger than the solid part of the circle, you don't touch the circle. You're still going to come back to Earth because gravity will act as your centripetal force, because that'll be the only force acting on you during this parabola here is just gravity. Okay, you won't feel any normal force, so you'll feel weightless even though you're not. Okay. All right, so this is kind of the diagram I was showing you there before. Okay, no matter where you are in the circle, gravity pulls equally, but it pulls in always downwards, towards the center at the top, out of the center at the bottom, okay, and on the sides just downwards. Normal force is always present as well, but it changes its magnitude depending on how fast you're going. And that's what gives you those different feelings of weight, okay, as you go through the circle. But obviously at the bottom of the circle, okay, is where you're going to feel the most normal force. So this is where we would feel G-forces, okay, is here at the bottom, or at least the most G-force. And the way we calculate G-force, and you'll want to write this down because it isn't on your formula sheet anywhere, okay, G-force is how many times greater normal force is than the force of gravity. That'll be a calculation you'll have to do in your West Ed assignment, okay, is to calculate G-forces. All right, so you take the normal force and you divide it by the force of gravity. In other words, your apparent weight divided by your real weight tells you how many times heavier than normal you feel, okay? If that force is really, really large, okay, that can be hard on the body, all right? It can cause you to black out like we saw with that guy in the G-lock video, okay? If you're a fighter pilot, that's where you have to be most concerned about blacking out, is at the bottom of a steep dive. Okay, everyone follow there? Okay, now there's all kinds of cool things you can do with this whole vertical circle thing. Cirque du Soleil did one a number of years ago when Cirque du Soleil Cusa was on tour. They had the double wheel. Okay, and that uses all these things that we're talking about. Okay, it harnesses all of them. When you watch it from a physics perspective, because Mr. Dickey actually had tickets, he went and saw it, and he's, when he got there, he's like, oh man, like I have to buy this DVD because I have to show this to all the physics classes, because as they go around on this ball, you can see when the forces change. You can see how that affects them. You can see that they become apparently weightless as they go over the top when it's moving fast enough. When it's not moving fast enough, they fall out of the circle. Okay, so you can see when they're at minimum speed, when they're faster than the minimum speed, when they're slower than the minimum speed. You can see all of those effects. So I'm going to show you that video. I want you to watch for those kind of times as the video goes along. All right, so is that kind of making sense how that vertical stuff works? Okay, so we'll be looking a little bit more at that here tomorrow. Mostly we'll look at problem solving, how these kind of problems are going to work. So that'll be the plan for tomorrow. We'll work mostly on that. Wednesday at the start of class, okay, we're going to be working on getting ready for West Ed. So we'll do some measurements, get our groups and stuff together, all that kind of stuff. That'll happen on Wednesday. And then the rest of Wednesday will be more vertical circular motion stuff, because we got to know that when we go to West Ed. Otherwise, some of the stuff doesn't make sense. Okay, so that's what's coming up. Right, keep that in mind.